Good morning.
Hello, Joseph. Hello, Satya.
Hello, good morning.
Good morning. So, can I start now?
Maybe we can wait for 1 minute.
Yeah. Is the AC on? On தானே? ஓ, அது இருக்குல்ல. கொஞ்சம் கம்மியாக கொஞ்சம் குட்டுவீங்க கொஞ்சம் நேரம் அதுக்கப்புறம் குறைச்சிடலாம். Thank you. Okay, so good morning to everybody. If there is any question, you can ask me now. Otherwise, I will start my 13th lecture. Lecture 13, and what was this? Development of I don't have to write the development. Gauge theory with spontaneous breakdown of symmetry. We have already done gauge theory, but now I am going to introduce breakdown of the gauge symmetry. Already we started doing it last time. In fact, I was doing what is called Goldstone model. I am just going to repeat it now. Goldstone model. The Lagrangian density is d mu phi minus lambda into rho squared minus phi squared minus phi 0 squared. I hope I wrote it in this form last time. I mean, by changing some parameters, I have introduced a new parameter phi 0 squared, which is minus mu squared 2 lambda over 2 lambda. Goldstone model is nothing but that mu squared, the case B, mu squared negative. So mu squared negative, so phi 0 squared itself is positive. I already did it, so let me repeat it now. The potential has a symmetry, a circular symmetry in field space. The potential is a minimum all along the circle and it's a maximum here. This is maybe I should. Remember, this is actually a complex file. So phi star is coming there, and even this is wrong. Phi squared minus phi 0 squared into phi star squared. Phi 0 itself is real. Square is lambda 5 power 4, which is actually phi squared into phi 0 squared, and then the cross term will give you the mu squared term, and then I have added a constant term so that the potential is lifted, so that there is no negative energy we have to deal with. So the potential is a minimum all along the circle and a maximum here. I said we should not choose this as the ground state. Normally, when mu squared is positive, the potential is like this, and we choose this as the ground state. This is mu squared positive and this is mu squared negative, because it is an unstable equilibrium. We should choose a minimum of the potential, and the model has a circular symmetry in the phi 1, phi 2 space, in the field space. Although this will be a symmetric point, that is not an equilibrium point, not a stable equilibrium. We should choose here. Any point along the circle is okay, but once you choose this point, then the circular symmetry is broken, because that is the ground state, and we will build all other states based on that, so that the circular symmetry is broken. That is the spontaneous breakdown of symmetry. And then I identified two modes. Instead of phi 1, phi 2, it is better to use polar variables. One, the phase variable, and one, the radial variable perpendicular to it. I call this the beta mode, and this is the alpha mode. And all along the alpha mode, you can travel without any expenditure of energy. Energy is 0 here. Potential is 0, so energy is 0. Since energy is 0, it is a massless mode. By energy here, we mean E equal to root of m squared c power 4 plus p squared c squared, the Einstein relation, because it's all relativistic quantum field theory, relativistic mechanics. So when E equal to 0, p also is 0 and m also is 0. So this is a massless mode. I think I should write bigger. And beta will be a massive particle. So as I already pointed out, if you had chosen phi 1 and phi 2 as the variables, it looks as if there is a tachyon here. Because mass squared is negative, it looks like a tachyon. People used to write papers on that, but all that is wrong. They have identified the ground state wrongly because it's an unstable equilibrium. If you identify the ground state correctly, and then instead of using phi 1, phi 2, you choose alpha beta as the field variable. We can always change field variables. Then you find that instead of phi 1, phi 2, which seem to have tachyonic mode, it is actually one is massless, the other is massive. And I said, I think I left it at this point. This is called the Nambu-Goldstone boson, or Goldstone boson simply. Nambu also did quite a bit of work on SBS. So in honor of that, although it was Goldstone who discovered this massless mode, after that they called it a theorem, Weinberg, Goldstone, and who is the other one? Weinberg, Goldstone, and Salam. Claimed they proved a theorem called Goldstone theorem, in which any spontaneous breakdown of symmetry will always lead to massless boson, and that is bad news for particle physics, as I said, because there is no such zero mass particle has been seen experimentally, and if it were there, there will be another long range force apart from electromagnetism and gravitation, which we know do not exist in the world. So there is no such massless particle, no such particle as Goldstone particle. So this was an obstacle to use the spontaneous breakdown of symmetry mechanism in particle physics for a long time. And it was Peter Higgs who showed that this is wrong, this theorem is wrong, there is no such theorem if the symmetry which is broken is a general symmetry, space-time dependent gauge transformation. That is what Higgs proved, and then only the progress could be made. But before I go there, I want to put whatever I have said here in mathematics. That can be done very easily. For that, do this phi 1, phi 2, you transform them into polar coordinates in field space. So phi is equal to rho into e power I theta. Rho and theta are real variables, I mean real fields. They are also space-time dependent, of course, these are all fields. So instead of phi and phi star, we have phi and phi star or phi 1 and phi 2, we have rho and theta, two real fields. I mean the system actually corresponds to two real fields, which if you write phi 1 plus I phi 2, phi is phi 1, they are the Cartesian decomposition, and this is the polar decomposition. Phi 1, phi 2 real, rho and theta also real. So substitute this into this Lagrangian. So this gives L is equal to, this calculation you can do very simply. Please do it. That's all we have. So there is a rho field, kinetic energy term for it, and rho interacts with the theta field, and then since there is a rho squared term here, rho squared into phi 0 squared into lambda, that gives a mass. See, remember in the Lagrangian way, the way to identify the mass of the particle, the quantum corresponding to that quantum field, is to look at quadratic terms. Quadratic terms with the derivatives will give kinetic energy of the particle, of the quantum, but quadratic term without any derivative, just quadratic term, coefficient of that is actually the mass squared. So we have the mass for the rho particle, but there is no quadratic term for theta. So theta is massless. So that means theta is massless. So that is the Goldstone mode, as I already identified. And the mass of rho is, we can, but before I do that, I want to do some transformation. Although rho is the proper field, it has a non-vanishing vacuum expectation value which is equal to phi 0. So it is better to subtract. So the ground state in classical theory is called the vacuum state in quantum field theory. The ground state of rho I will denote by this vacuum expectation value, and that is equal to phi 0, which has to be a constant. Actually, we have chosen it to be a constant, because if it is not constant, then all the space-time symmetries, etc., will be lost. Physical space is translation invariant, both in space and time, and rotation invariant, and hence any property we ascribe to vacuum has to be constant. So this vacuum expectation value has to be constant, and you subtract that and define a new field eta as rho minus this rho vacuum expectation value, because eta itself vacuum expectation value is 0, so it is a normal field. It is easier to treat eta. It is a constant you remove. So let us rewrite this as d mu eta plus eta plus phi 0 square d mu theta minus lambda. Now I am going to expand this. First of all, write rho as rho minus rho vacuum expectation value, namely rho minus phi 0, rewrite this in terms of eta, then 4 phi 0 squared. These are all simple steps. I am sure all of you can understand this. So the eta field, massive field, has a mass, you can see, because there is a quadratic term. These are all constants. So this is the coefficient. Here is the mass squared of the eta. I think there are factors of half and half or 2. So m eta is equal to 2 root 2 into lambda into phi 0. So this massive particle has this mass. So I have just repeated whatever I said in terms of mathematics here. That's all, to make it completely clear. As I said, this is not the model which we want. Higgs gauged this, namely he introduced a gauge field so that the theory is invariant under general phase transformation. This theory is invariant under constant phase transformation, namely phi equal to e power I alpha into phi. Alpha is constant, as we know. So this is also U1 theory, but it is a constant U1 theory, special U1 according to our terminology. Now I want to make it general, and we know how to do it. So that is the Higgs model. This is the Goldstone model. Now I am going to Higgs model. Lagrangian is, remember, once I make it space-time dependent, the Lagrangian will not be invariant unless you add a gauge field, which also gets transformed. All that we have done. I am just taking over those tips. The main point is the derivative gets replaced by the covariant derivative d mu minus IE a mu phi star d mu plus IE a mu phi. So the kinetic energy term gets replaced by the covariant derivative terms, and then we have to add the dynamics of the a mu, which is just the usual f mu nu into f mu nu, which I will write in terms of a square of this. By square I mean these are indices coming here. Let us put everything down. This multiplied by the same thing, but with the indices above, then only it is relativistically invariant. Remember, because of the G mu nu, which is not a unit matrix, but the -1, because of that, this complication of lowering and raising is there. One lower index can be contracted only with one upper index, and repeated indices are summed over. That is called contraction. So these are all this into the other one. Here also, I should have put here like this. So this is called contraction. What does contraction do? Contraction takes out vectors and forms scalar products. That's what contraction is. And it can remove some indices from tensors and make them into vectors, and further vector into vector. If you contract the indices with the G mu nu, then it becomes a scalar minus the potential term this is the way I should have written. I don't know why I wrote like that. Please change this phi star minus phi 0 squared then I can simply put square. 35 I should have. Okay. Now I am going to again make some change of variable for the fields. Namely, phi I am going to write as, sometimes if I write phi like this or sometimes like this, for me it is the same, rho into e power I theta a mu is equal to b mu minus 1 over e into t mu theta. I simply substitute this. You know what will happen if you substitute, because this is like gauge transformation, theta is like the alpha x, and remember this is gauge invariant. So when you substitute, the alpha dependence will go because Lagrangian is invariant whatever may be alpha. So by the same token, this theta which I have introduced will disappear. So the Lagrangian is the same. Lagrangian which was written in terms of phi and d mu, I am going to rewrite in terms of Lagrangian in terms of rho and d mu. That is the transformation I make. And in that transformation, theta disappears. This transformation is like the gauge transformation, which we already know. This is a gauge transformation which we already know, and it is like that. So this will look like a gauge parameter. So as far as mathematics is concerned, it is like a gauge transformation. So the gauge parameter disappears. In that process, the field theta disappears. So L, the new L is d mu rho minus IE b mu into rho, and d mu rho plus IE b mu rho. Of course, this transformation, since this term is invariant, okay, this is a curl, this is the curl, but any derivative, the curl is invariant under addition or subtraction of a derivative term, and you can explicitly see that this will vanish when you take this minus, and hence this is nothing but d mu b mu minus d mu b mu square. Square means proper relativity combination, contravariant vector, covariant vector multiplied by the contravariant vector, and summed over indices, and then finally lambda. There also the theta will go, so only rho will remain. So this is the transformation. I have only made a transformation because of the gauge invariant nature of this. The transformation removes this field theta. Remember, theta is the troublesome Goldstone boson. Theta is gone. Actually, what has happened to theta I will now describe. Again, do the same things which we had done earlier, namely replace rho by eta, rho minus the vacuum expectation values, make that substitution. So the Lagrangian density becomes d mu eta, d mu eta. I am now going to write down everything explicitly. I am going to work out this product, plus E squared phi 0 plus eta whole squared b mu minus 1 over 4 d mu squared minus lambda 4 phi 0 squared eta squared plus 4 phi 0. This is like what we did earlier, this term. there is a mass term for eta which is exactly the same as before, we can write down. But more important thing is, remember in this Lagrangian, I cannot write down a quadratic term for mu. Suppose I write m squared. If you have to add a mass to the photon, the quantum electrodynamic Lagrangian should be changed by addition of this m squared mu. As I said, the quadratic term denotes the mass for the quantum. But photon is massless, so we don't add. Actually, we cannot add this because this will not be invariant. Remember, this term will not be invariant under this. So we cannot add mass term. That is why gauge invariance is in electrodynamics is what dictates the photon to be massless. But now see what has happened in these transformed variables. There is a quadratic term for b mu, a constant term, namely E squared phi 0 squared is really the mass. So let us identify the mass particles. First of all, this eta, that is the same mass as before, I think. 2 into root 2 lambda into phi 0. The important point is B meson, I mean the B quantum, the vector particle, since it is a vector particle, it is spin 1 particle, MB is square root of this coefficient of B mu, which is root 2 E into phi 0. This is what is called Higgs mechanism. So that the vector particle, the spin 1 particle now is massive. Now, where did it get mass from? See, actually we said theta is gone. So what has happened is, in all these funny tricks which we played, theta has gone and got absorbed into mu. Mu, which was massless, comes out with a mass. Mu devours the Goldstone boson, comes out with mass. And remember, electromagnetic wave has got only two polarizations, and when in the quantum version, that corresponds to the photon having only two spin directions, either spin in the direction of the propagation or in the opposite thing. But I said photon is spin 1, but it has only two spin directions. Please remember that a spin 1 particle should have only should have 3 according to angular momentum theory, which everybody studies in non-relativistic quantum mechanics. But this spin 1 particle has only 2. You should ask the question, how does it escape the angular momentum algebra? The point is, angular momentum algebra is not applicable to the intrinsic spin of photon. Intrinsic spin is always the angular momentum in the rest frame of the particle. Photon does not have a rest frame, it is always moving at speed of light. So you cannot have a rest frame. So the usual angular momentum algebra is not applicable to photon. Some other algebra called E2 or E3, I don't remember, is applicable, and that allows photon to get away with just 2 components. So at this stage, before the symmetry is broken down, this quantum has only 2 directions. In the wave theory, it is 2 directions of polarization. In the quantum theory, 2 directions of the spin. But this is a massive particle, you can go to the rest frame. So it should have 3 components, and this extra component, the longitudinal component, is really the theta. Theta becomes the longitudinal component of the B, and that is why we say that B actually devours the theta and comes out with a massive particle. Okay. I think that's all I have to say about this particular model. This was the original Higgs model, and it was generalized to non-abelian gauge theory by Kibble. Kibble is the one who made that important contribution, but again, Nobel Committee made a mistake by omitting Kibble in the list of Nobel Prize winners. It is only after Kibble wrote the paper that Weinberg and Salam could construct the correct electroweak theory, because electroweak theory depends on non-abelian gauge theory. So I move into now non-abelian gauge theory and its symmetry breakdown. But at this stage, if there is any question, I can answer.
So the symmetry breaking.
Yeah.
Here the symmetry of the Lagrangian is not broken, right?
No, yeah, exactly. That's a very good point. The Lagrangian, we did not add anything which breaks the symmetry. We made some transformations, but the symmetry is inherent in the Lagrangian. So only the equations of motion. I mean, only the solutions, not even equations of motion. Although the theory is symmetric, it allows asymmetric solutions, and we pick the asymmetric solution. Remember, in that circle, we choose that point, which allows us to choose. So it is the spontaneous symmetry breaking is symmetry breaking of the at the solution level, not the Lagrangian, and that is very important.
So picking up a particular solution depends on what? Is there some fluctuation that will drive it to one of the possible solutions?
All that will happen, but that will lead to further physical phenomena. So I will not go over into it. Actually, the formal quantum field theory says that the vacuum is a degenerate vacuum. There are infinite number of vacua. We have picked one. So it leads to a lot of other mathematics, but I will not go over all that, because that is all unnecessary for understanding at this level. Okay? Yeah. So now let me go to SU2 gauge theory, which is already done, but we want to do SU2 gauge theory with symmetry breakdown. SU2 gauge theory I had done using Dirac field psi1, psi2, but now I want to do it using the Bose fields phi1, phi2. So there is a doublet phi1, phi2. Actually, there are 4 fields here. This is SU2 doublet, I equal to half doublet, and each of them is complex. So 2 components here, 2 components here. There are 4 real components. And what is SU2 rotation? The SU2 transformation on this you already know. Apply the unitary transformation. Phi goes to exponential of I tau by 2 dotted with alpha. Alpha 1, alpha 2, alpha 3. This is a vector scalar product notation in isospin space I am using. Alpha 1, alpha 2, alpha 3 are 3 constants. Into phi. This is a unitary unimodular transformation. So let us call this as U. This is thereafter I will call simply as U. And you can see that phi dagger, you take Hermitian conjugate of this. What does Hermitian conjugate does it? The column vector becomes a row vector transpose, and then phi 1 star, phi 2 star come. That is phi dagger. And you can see that phi dagger phi is invariant. If you apply U, will come here, U dagger will come here. Since U dagger U is 1, phi dagger phi remains invariant. So the Lagrangian density, again the steps are similar to what we did for the phase transformation, and the phase transformation we called it U1. So Higgs model is for U1 actually. Abelian gauge theory only he did. Although I used A mu, it is not the electromagnetic potential because we don't want to break the electromagnetic gauge symmetry. Finally, even in the standard model, electromagnetic gauge symmetry is not broken, photon remains massless. So, this is just a toy model which I have constructed. I am constructing one or two toy models before I construct the actual standard model. L is d mu phi dagger, d mu above minus v function of phi dagger phi. Instead of phi star phi, now phi dagger phi. It will have the same form as before, that phi dagger phi minus phi 0 square, whole square. That's all that is. So, this is invariant under the constant transformation, what we call the special SU2. That is clear because since alpha is constant, the derivatives don't do anything. So, phi dagger phi comes here. So, here also phi dagger phi only depends. So, the whole Lagrangian is invariant. Now, I go to general SU2, first special SU2. Next general SU2. Namely, the alpha alpha 1, alpha 2, alpha 3 now become arbitrary space-time dependent functions. So, phi prime is equal to e power I tau by 2 alpha space-time dependent function into phi. And in order to make this invariant, because derivatives are there, we have to cancel the derivative terms on alpha by introducing gauge field. How many gauge fields we have to introduce? There was one gauge field for U1, and here 3 gauge fields. Remember, these components correspond to the number of generators. Number of generators for SU2 is 3, so the number of gauge bosons are 3. So, introduce 3 fields. Again, we can call it vector, or in terms of components, W mu I going from 1 to 3. And at this point, of course, algebra becomes more complicated. I did it last time for the non-abelian gauge theory, and best thing is to introduce W mu in the matrix form, 2 by 2 matrix form, which is obtained by multiplying by the Pauli matrix. This please remember, although I write simply W mu, it is a matrix now. Instead of writing it as 3 vector components, we write it as a traceless matrix. A traceless matrix, remember, has got only 3 components. So, this is the gauge field now, and I also introduce the field tensor G mu nu, which is a curl, 4-dimensional curl, plus the important quadratic term. I introduce just as I had a coupling constant E, which is really not electric charge, we can call it some other constant. Here I have to introduce another constant, small g, and the commutator. Remember, we did lot of calculations with this. I'm sorry, commutator. Those are matrices. And also we introduce the covariant derivative, namely d mu minus Ig. So, W transforms, W will transform, I have not written down the transformation, you can write down. Covariant derivative after transformation and phi goes to phi prime. I have not written down the transformation, but you can take it from the last term's notes, is equal to, it's a covariant derivative, so the phase factor comes out and without any derivative term. That is the point. Although alpha is space time dependent, the derivative of alpha gets cancelled. Or maybe I can write it down. I don't know whether the transformation corresponding to phi W mu prime is equal to, the same u will come, W mu u minus or plus, please check, 1 over G u d mu, this is u inverse. That is the transformation. This is the generalization of the usual transformation which we had in the case of U1 theory. See, what is a U1 transform, U1 abelian transformation, all these commute with each other. So this is nothing but a W mu, and in the case of abelian transformation, you can write down d mu alpha into exponential, which is u inverse, and that u inverse and u will cancel each other, only d mu alpha will remain in the case of abelian. So this is the general gauge transformation on the non-abelian gauge field, which in some sense incorporates even the abelian one, which is much simpler. So I have defined everything now. So the covariant is called covariant derivative because the transformed thing has only a phase transformation. I mean a phase factor, no derivative term. So the Lagrangian can be written down. Let me first write down the gauge field term, minus 1 over 4. Remember all this we did earlier. G mu into G mu. And this remains invariant under this transformation. When you make this transformation, so G mu will also get, actually what happens is under this transformation you can prove that G mu, in fact it took long time to prove it, remember lot of terms were there. G mu prime is equal to u G mu u inverse. Lot of terms were there, they all cancelled. So the gauge field vector, the vector gauge field has two terms, derivative term and this term, whereas the tensor gauge field has only this term. This is analogous to what happens in the U1 theory. In U1 theory, remember f mu nu does not transform at all because this into this will be 1, and so it does not transform at all, although a mu has a derivative term. Here the corresponding generalization is this, u will always come, and by substituting this into this you can see that this is invariant. Now I am going to write down the covariant derivative. This vector means it is not a vector. This arrow denotes for me that this derivative, although I have written derivative, it operates only on this left side. So this is a notation which is convenient. Of course, there are other ways of writing this also. okay, and this is invariant. Under the general SU2 transformation.
You have to also write a phi there, no?
Where? Oh yeah.
This phi dagger.
Yeah. Here phi dagger and here. Yeah, sorry. Yeah.
And you have to put a right arrow or tell me.
This is right arrow, usual arrow. Usually when we write derivative, it acts only on the right. So here only I depart from convention, and so I explicitly indicate by this. Okay. There are other ways of writing it, writing phi dagger here, but then remember the matrices are there. So here actually this matrix, remember this is a 2 by 2 matrix. WM is a 2 by 2 matrix now, and that has to come to the right of this only. That is why it's rather inconvenient, but we have to do it. So let us go to the symmetry breakdown of SU2 symmetry. First again special SU2. Namely same model, I am not repeating everything. To reveal the symmetry breakdown, it is better to, and remember we have chosen this form with mu squared negative, so the phi will pick up a vacuum expectation value. That is what induces spontaneous symmetry breaking. So that is why this term is very important. Remember phi 1, phi 2 together make up 4 real fields. Now I decompose, the polar decomposition here is like this. This is the kind of thing which Kibble did it very generally actually. I am applying it to a particularly simple case. Rho theta 1, theta 2, theta 3 has 4 real fields. Instead of the 4 real fields contained here, I have now chosen this is the polar decomposition to be used, because this is a complex doublet. Which corresponds to 4 real fields, again 4 real fields. So now we have to plot, but plotting now becomes very difficult, because instead of the circle which was just characterized by one parameter theta, here there are 3 theta. So the manifold of minimum potential is 3-dimensional. You can imagine it easily, there is no problem. So so what we have done is phi 1, phi 2 complex. We have gone to theta 1, theta 2, theta 3, rho, all real. So we have to plot the potential, but remember that minimum potential manifold has 3 dimensions characterized by 3 angle type of fields, theta 1, theta 2, theta 3, and the potential will be 0 there. Since the potential is 0, exactly like the potential was 0 along the minimum of circle. Circle was 1 dimension. Here we have to generalize, think about it, about the generalization to 3-dimensional minimal surface. But we can move over anywhere in these 3 dimensions. So there are 3 modes which cost 0 energy in movement, and hence they correspond to Goldstone bosons. So there are 3 Goldstone bosons here. Once you identify the angle type of variables, you know how many Goldstone bosons are there. 3 massless. So let me say the minimum of V occurs over a three-dimensional surface, and that is therefore there are three massless Goldstone bosons. Theta 1, theta 2, theta 3 will correspond to massless bosons, and one will be real, so that will be massive, and one massive scalar boson. Scalar boson means spin 0 scalar boson corresponding to rho. Corresponding to rho, rather the rho minus rho vacuum expectation value, which is phi 0. That is what I think we are going to call it eta. I don't know what we are going to call it here. Okay. So let us quickly do this general SU2 now. General SU2, how do you do it? Yeah, the Lagrangian is there. In that, we again make the same substitution. What looked like a gauge transformation now becomes a change of variable. So substitute phi equal to e power I tau 8. And also W also we have to make in terms of W prime, and so rewrite this in terms of W prime, and so let me simply say W goes to W in terms of here phi in terms of rho and theta, W in terms of W prime. W prime is defined here. That will contain the thetas. Remember now U this is U, so this will contain the thetas. And we know the result. So let me write down the result. The result is that these thetas will disappear because there is gauge invariance in this. What we called alpha, the gauge parameter, now is taken over by the theta fields. Just as the when you make the substitution, the resulting Lagrangian does not depend on alpha. That is what is meant by gauge invariance. By the same mathematics, this Lagrangian rewritten in terms of this will contain everything, but theta will disappear. I mean, that algebra you can do, but there is no need because we already know what it will be. W's will be that. I don't know whether this is correct, but let me write down here. Minus, see now instead of using this notation, arrow going in, derivative acting on the left, let me now go to another notation for writing this. 1/4 G squared. I don't know why I am writing like this. D mu minus Ig tau by 2 dotted with W mu prime 0 rho. See what I have done. Instead of phi or phi dagger, I simply write only 0 rho because thetas are supposed to have disappeared. So now everything is in proper order. The derivative operates on this, and 2 by 2 matrix operates on this column vector. but we have to take the Hermitian conjugate of the whole thing into the other one, d mu minus Ig I think there is something wrong here. I am mixing up notations. Instead of W mu vector, we introduced the matrix by absorbing tau by 2 in that, minus Ig W mu 2 by 2 matrix. Same thing here also. Okay, that is the kinetic term. Now, what is this? This is into 0 rho. Okay, minus lambda rho squared by 0 square rho square. So, that is the Lagrangian. So, what has happened? As expected, the theta 1, theta 2, theta 3 have been eaten away by the W fields because there is no theta 1, theta 2, theta 3, no theta 1, theta. Goldstone bosons have disappeared. So, this is the final result. Well, instead of W, now we can even remove the prime if you want, but for the moment we keep, because that is now the physical field. Now, of course, this will produce a mass for the rho field, or rather the eta field. Eta is rho minus vacuum expectation value of rho, and there is now quadratic term for W, because remember W squared is coming here. Where is the quadratic term? Yeah, because remember this rho has to be replaced by rho minus phi 0. So, there is a constant term here. It is that constant squared into W prime squared. That is the mass term for the W prime. We can identify the mass term, all that we can do, but there is a little bit of algebra which is needed. So, I will do it, I think, after a break now. I want to rewrite it in another form, rewrite that commutator in another form. But if there is any question, you can ask me.
When we have this phi 1, phi 2 we started.
Yeah.
A doublet like phi 1, phi 2.
Yeah.
This correspond to two different fields correspond to two different particle fields, right?
Actually, you can say 4 particles, right? Because phi 1, phi 2 are complex. So, phi 1, phi 2 particles and their antiparticles. So, there are 4 particles originally.
Yeah. So, when we transform it into this 0 rho like that, when we write.
Yeah.
What actually is physically that represents? That means there is a these two fields.
So, these two, see, if we use these original fields, they will look like tachyonic fields because negative mass squared comes. Okay. So, since we want to go to an asymmetric vacuum point, it is better to reveal the real particle content by doing some field transformation. So, we have made a field transformation, the so called polar components, and the polar components are theta 1, theta 2, theta 3 and rho. And the polar components tell you that theta 1, theta 2, theta 3 are massless, and rho, or rather rho minus phi 0 is a massive particle. But then when we go to the gauge diversity,